Welcome back. In this video, we are going to move past the simple 3D cube and extend the model class to be able to read in model data using the Wavefront object file format. Up until this point, we've hard-coded our model data directly into our code. This is time-consuming, inflexible, and prone to errors. It would be much better if we could specify all model data in a separate file that could be loaded in at runtime. The Wavefront object file format is an open geometry definition file supported by most 3D modeling programs. A V indicates a vertex position, Vn indicates a vertex normal, and Vt a texture coordinate, with the subsequent values being the x, y, and z component values. So for example, the Wavefront object file for the cube we've been rendering in the previous tutorials may look something like this. The first 8 values specify the 8 vertex positions, one for each corner of the cube. Then we have 14 texture coordinate values. These indicate how a 2D image would get mapped to cover the surface geometry of the model. And finally, 6 normal values, one for each face of the cube. I will explain in more detail in the upcoming tutorials the purpose and use of vertex normals and texture coordinates. The final portion of this file format that we care about lists how to construct each individual face, which for our rendering pipeline will all be triangles. Each face of the model will be listed on a separate line that starts with the letter F, and will consist of 3 face elements, one for each vertex of the triangle. A face element is made up of index values. The first value is an index into the list of vertex positions. So for the first triangle, we want to use the 5th vertex position value. Then following the /, the next value is an index into the texture coordinate list. So the first texture coordinate value, and then, as you can probably guess, that leaves the last value of the face element as the index into the list of normal vectors. Therefore, the first vertex of our triangle is given by 1, -1, 0.875, 0.5, and 0, -1, and 0. To construct the rest of the triangle, we do the same for the other 2 face elements. So the explanation I have provided here is a simplification of the full file format specification. I've ignored materials as well as some other details. For more information, check out the Wikipedia article on the topic. Rather than write our own code to read in this file format, we will make use of TinyObjLoader, a single-file Wavefront object loader written in C++. So let's start by adding TinyObjLoader to the project. Follow the link in the description below to navigate to the Git repo for TinyObjLoader. You can download the entire master branch, but really all we need is this single header file. In my development folder, I have a directory called libs, and I will create a new folder called TinyObjLoader. Then back on GitHub, I'll open the raw version of the file and save it to the TinyObjLoader directory I just created. When saving the file, make sure you don't accidentally include an extra file extension, such as txt. Next, we need to include TinyObjLoader to be built with the rest of our project. How you do this will differ depending on how you build your project. I am using a makefile, so I first need to add the path to the directory I just created into my .m file. So tinyObject path is equal to users brendan dev libs tinyObjLoader. Then in my makefile, I will add the tinyObject path to be included in with the C flags. And that's it. One other thing you might want to do is if you are using VS Code is add this to the include path of your C++ properties.json file. This way the code completion will work correctly within the VS Code editor. Setup for Visual Studio on Windows is pretty similar. Create a folder in your libraries directory called TinyObjLoader, and then save in it the tinyObjLoader.h file. Then in Visual Studio, navigate to Project, Project Properties, and in the C++ settings underneath in the general heading, we can add the path to tinyObjLoader to additional include directories. So click Edit and add a new entry inputting the folder's path. Now let's quickly test that we've included TinyObjLoader correctly before progressing with the rest of the tutorial. Open the model implementation file, and near the top, first define TinyObjLoader_implementation. You only want to have this defined in a single CPP file within the entire project. The define signals to the preprocessor that this file in the project will contain the implementation for TinyObjLoader. Then include TinyObjLoader.h in angle brackets, and you can build and run your code. If things are still working, that means TinyObjLoader has been successfully added. Finally, I've provided some model files to get started with. Follow the link to my Google Drive, open the Models folder, and click Download All. Unzip the folder and copy it to your project directory. Okay, let's get to coding. Open your model header and extend the Vertex struct to also support normals and texture coordinates. Add a field of type GLM vec3 called normal, followed by a GLM vec2 called UV. UVs is just another commonly used shorthand for two-dimensional texture coordinates. Then, inside the builder struct, I'm going to declare a void loadModels function that takes a const std string reference called filename as the argument. Following that, let's create a helper function to create a unique pointer model object. So first include the memory header, then inside the model class, declare a static function that returns an std unique pointer of LVE model type called createModel from file. And this will take an LVE device reference called device and a const std string reference called filePath. Let's copy this function declaration and head on over to the model implementation file. I will paste the function in, add my class name scope, and remove the static keyword. Then inside, I'll initialize a variable of type builder called builder. Next, call the builder.loadModel function, passing through the filePath argument. And then return std makeUnique of type LVE model with arguments device and builder. I'm going to include IOStream and then add a print statement that logs builder.vertices.size. This way, for now, we will be able to see how many vertices a loaded model contains. Next, we need to implement the loadModel function. So at the bottom of my file, but still within the namespace, I will add void LVE model builder loadModel with the argument const std string reference filePath. Then declare a local variable with type TinyObject::attrib_t called attrib. Next, an std vector with type TinyObject_shape_t called shapes. Then another vector but with type material_t called materials. And finally declare two std strings called worn and error. All of these values will be set by TinyObjLoader and will store the results of reading a Wavefront object file. So in an if statement, we will have not TinyObjLoadObject with the arguments reference to attrib, reference to shapes, reference to materials, reference to worn and error, and finally filePath.cString, which provides a car pointer representation of the string variable. If we fail to load the object, we'll throw an std runtime error with worn plus error as the output. So following this loadObject function call succeeding, these local variables we declared should now be initialized with the data from the .obj file. The attrib variable stores the position, color, normal, and texture coordinate data. The shapes variable contains the index values for each face element, and the materials we will ignore for now and leave to a future tutorial. Okay, so we've got our data. First, let's call vertices.clear and indices.clear to start from a fresh builder state. Then add for const auto reference shape in shapes. followed by a second for loop with const autoreference index in shape.mesh.indices. This loops through each face element in the model, getting the index values. Inside the for loops, declare and initialize a vertex local variable. Let's start by setting the vertex's position field. To do so, we should first check if index.vertexIndex is greater than or equal to 0. The vertex index is the first value of the face element and says what position value to use. Index values are optional, and a negative value indicates that no index was provided. If a vertex index is provided, then we can set the vertex.position equal to curly brackets attrib.vertices at an index of 3 times index.vertexIndex plus 0. Each vertex has 3 values that are tightly packed into the attrib.vertices array. So to read the corresponding position, we need to multiply by 3 and then add 0 for the initial component. Then duplicate this line twice, updating +0 to +1 and +0 to +2 for the positions y and z components respectively. Now reading the normals and texture coordinates is all very similar, so I'll duplicate this entire if block and paste it just below. Change each occurrence from vertex index to normal index, vertex.position to vertex.normal, and attrib.vertices to attrib.normals. And repeat this one more time for the texture coordinates. Change each occurrence of normal index to textchord index, attrib.normals to attrib.textchords, and vertex.normal to vertex.uv. The only other notable difference is that the UVs are 2 components rather than 3. So remove the last component and change to using 2 times index.textchord index. And then we can add this vertex to the builder's list of vertices with vertices.pushbackVertex. And that would be pretty much it, except we haven't handled colors yet. And that is because the Wavefront object file format doesn't actually support them. However, there does exist an unofficial extension that is supported by TinyObjLoader. Some applications support vertex colors by putting red, green, and blue values after the X, Y, and Z vertex position components. I've included a colored cube object file to demonstrate this feature. So inside the if block for vertex index, we can extend it to add color support. First, I'm going to calculate the last color component's index value and store it in AutoColorIndex is equal to 3 times index.vertexIndex plus 2. Then check if color index is less than attrib.colors.size. We use the last index because color attributes are optional, and this is a convenient way to check that a color has been provided and the index is in bounds. If this is true, then we can initialize the vertex.color field. This is pretty much what we had before, except each component is equal to attrib.colors rather than attrib.vertices, and rather than +0, 1, and 2, we instead have color index -2, -1, and -0. Finally, add an else statement setting the vertex color to some default value if no color has been provided. Okay, now all that's left to do is load in a model and render it. Open the app implementation file, and we can get rid of the createCube model function. Then in load game objects, change createCube model to LVE model create model from file, passing in the device and models/coloredcube.obj. Note that this is a relative path. If you run into an error, try using an absolute file path instead. For example, this is what I use on my Windows machine. Build and run your code, and we get a rainbow colored cube. That's because each vertex only specifies one color, and then the fragment color is interpolated across the face of each triangle, just like in tutorial 7. If we wanted a model to look like the previous 6-colored cube we had, we would need to duplicate each vertex position twice, so that we could specify a different color per face. Now let's try a more complex model. Update the file path to load the smooth vase object file. If you build and run, this appears kind of small, so I'm going to change the transform.scale to equal glm vec3 with a multiplier of 3. And I will also rename the cube local variable to be GameObject, as that's a bit more applicable now. And there we go, we have a nice white vase with a vertex count of 30,888. However, even with so many vertices, you can't really see anything because the entire object is just painted white. To get something with visible detail, we need to apply lighting, which we'll do so in next week's tutorial. So we've successfully loaded in a model using just vertices, but we didn't make use of the index buffer that we added just back in the previous tutorial. Index buffers are a great optimization for reducing the memory required to store complex 3D models. So we definitely want to be able to use them when loading objects from a file. But one thing you've probably noticed is that each face element definition can use a different index value for the position, texture coordinate, and normal. But in Vulkan, we can't do this. We can only have a single index buffer, and we need all the values that make up each vertex to be grouped together. So creating an index buffer isn't quite as straightforward as just reading in the face element's index values. The purpose of an index buffer is to avoid having any duplicate vertices within the vertex buffer. As each face element is processed, we need to come up with a way to detect if we've encountered this vertex value before. If the vertex is new, we add it to the vertex buffer and add its position in the list to the index buffer. If the vertex already exists, then we can discard it and add the index of the existing vertex into the index buffer. Once every face element has been visited, we will be left with a list of unique vertices and a list of index values pointing into the vertex list indicating how to construct each triangle that makes up our object. This method I have just explained is the exact method provided by vulkantutorial.com. So if you found my explanation hard to follow, check out the loading models tutorial linked in the description below. To quickly be able to check if a vertex is new or has been seen before, we will use an std unordered map, which requires we provide a hash function that can take all the data in our vertex struct and map it to a single fixed-sized value. The unordered map can then use this hash value as the key to look up the vertex's position in the list of vertices. So first let's create a new file called lveutils.hpp. I've included this function in a pastebin link below. This is a function that can combine an arbitrary number of hash values together. Hash functions are kind of a complex topic, and I assume most of you guys are already familiar with how unordered maps work, so I'm not going to delve into the details of why this will work well. It's based on a Stack Overflow answer in the link provided. Note that it makes use of fold expressions, which is a C++ 17 feature. Okay, now in the model header, we need to overload the equality operator for the vertex struct. So add bool operator ==, const vertex reference called other, mark the function const, and then we simply check that all the struct fields are equal. So position equals other.position, color equals other.color, normal equals other.normal, and UV equals other.UV. Then in the model implementation, scroll to the top and include lveutils.hpp. In addition to the equality operator, we need to implement a hash function for the vertex struct, which will make use of the hashCombine function we just wrote, but to hash the individual GLM vec components, we need to include the GLM hash functionality. This functionality is technically experimental and subject to change, so we first need to define GLM enable experimental. But in practice, the GLM library is very stable, so I don't think this is something to really worry about. Then include glm gtx hash.hpp. Finally, we also need to include unordered map. I am going to inject a hash function for the vertex struct into the std namespace. So just following the include statements, but outside the lve namespace, I will add namespace std, followed by template angle brackets. Next, we declare a struct called hash with type lve model vertex. Inside, we need to overload the function call operator. So we have return type size t, then operator brackets, and as the operator function calls argument, we have an LVE model vertex const reference called Vertex, and also mark the function as const. Initialize a variable of type size t called seed equal to 0. This will store the final hash value. Then call LVE hashCombine with the arguments seed, vertex.position, vertex.color, vertex.normal, and vertex.uv. And then finally return seed. With this, we can now take an instance of the vertex struct and hash it to a single value of type size t, which can then be used by an unordered map as the key. Okay, scroll down, and in the loadModel function, let's initialize an empty std unordered map, using vertex as the key type and a uint32t as the value type. And I'll call it unique vertices. This map will keep track of the vertices which have already been added to the builder.vertices vector, and store the position at which the vertex was originally added. Then scroll down to the end of the function, but still inside the for loops, and replace vertices.pushback with if unique vertices.count of vertex is equal to 0. Then unique vertices at vertex is equal to static cast uint32 type of vertices.size. Then also call vertices.pushback vertex. So what this does is if the vertex is new, we add it to the unique vertices map. Its position within the builder's vertices vector is given by the vertices vector's current size. Finally, after the if block, call indices.pushback unique vertices at vertex. With this, we add the position of the vertex to the builder's indices vector. And that's it. We can build, run, and see our vase object once more. The big difference is that the vertex count has been reduced from 30,888 to just 5,545. By using an index buffer, we're saving a lot of GPU memory. As a final step, let's clean up IOStream and remove the print statement. Before you go, I would like to mention that we have a Discord. It's a great place to share code, get feedback, and meet like-minded people who are also crazy enough to try and make their own game engine. So if that is something you would like to join, links in the description below. Thank you for watching and keep on coding. Cheers.